I'm going to be taking you all through a deeper dive into some of the searches that are available to you, and this topic is specifically going to be on doing a JWST science instrument keyword search for exoplanet spectra. This is the notebook that we're going to be going through today. This is available to you in this repository, so you should have been dropped into a folder, this JWebbinar folder here. Under that, you'll find a folder called MAST. We are working on the exoplanet Spectra, so you can go ahead and click on that folder. And there's actually two notebooks in here. The live version is the one that I'm going to be working in that does not have the code filled in because I'm going to do a live type along. And then there's this exoplanet Spectra notebook here that's available to you for reference. It has all of the code in it and ready to go. If you wanted to play around with that, you're more than welcome to, or if you wanted to follow along, you can open the live or just watch me code. It's entirely up to you. Okay, so with that logistics stuff out of the way, if you are going to follow along in this notebook, please make sure at the upper right that this says JWebbinar. If you see something that says Python 3, you're not going to have any of the pre-installed packages available to you, so you're going to want to make sure that you switch this over to JWebbinar. And it should say that, but on the off chance it doesn't. Okay, with that, let's sort of get into the substance of this search. So as I mentioned, we're performing a science instrument keyword search for exoplanet spectra. And our search is going to take two forms. So for the first part of our search, we're going to use the MAST class of our API. So we're going to use this API for both searches, this astroquery.mast. That's our Python API to access the archive. The first half of the search, though, is going to be using specifically this MAST class. Now, it's a very powerful tool, and in fact, we're going to be performing a search that is difficult, if not impossible, to perform with our more user-friendly APIs and with a lot of our search interfaces as well. And we'll be using that tool, like I said, to actually find these exoplanet spectra. Some things to note about this is that it's only going to, when we perform this search, because we're searching on those science instrument keywords that come from FITS headers, we're only going to be searching on the actual FITS products themselves. And generally, these products are only going to be the more highly calibrated products, so levels 2B and up, and level 3, that is. Now, our other type of search that we're going to perform is using the observations class. So this is the more user-friendly version of our API, and it's going to allow you to search for data products that match a wide range of metadata values, but those are going to be somewhat limited. It's general purpose. It's not tuned to any particular mission. So with that, I think let's go ahead and jump in to this MAST class search. We're gonna talk a little bit more about these two things and how they're different and why you would use one over the other as we dive into this. So let's just go ahead and get started with our search. To begin with, imports always kind of have to do this, right? So there's a couple packages that we're going to need. As I just mentioned, astroquery.mast is our API, so we'll need that. We're going to need AstroPy for a couple things to handle tables, to handle reading FITS files, to handle formatting time correctly. And then we're also going to plot some things at the very end, so we'll need that import too. All right, part one, our search for exoplanet spectra. So this search is focusing on nearest spectral time series observations taken of transiting exoplanets. The data that we're using are from commissioning and early release programs, and they're all public. Just makes things easy. Everything has been out there. And nothing is proprietary. When we perform this search, we're going to have to use a very particular syntax. So as I mentioned, this MAST class is a little bit less user-friendly than some of our others, some of our other APIs, that is. And to get around that, we're going to write some helper functions. The details about why we need this syntax and what's being expected are available in these links here. So I do encourage you to come back and check this out after the webinar. But the basics of these functions here is that we need one to help us set parameters because it requires this particular parameter name P, values V, syntax when you're specifying the search. And then also because I don't happen to know what today's date is in modified Julian date. So we've written this function that will allow us to enter things in the traditional, or I guess the recognizable ISO format and convert those into modified Juliet date. So I'm going to go ahead and run those. And we can jump right into our first cell here. So in this cell, we're going to be setting up the keywords, one of which is the timestamp, but that's not the only keyword that we're going to be setting up. So we'll start by creating this dictionary. And I'm going to start with our first keyword, which is category. Now, all of these keywords that I'm typing out, you can find some descriptions of them here in this field descriptions of the JWST instrument keywords, and then the full JWST keyword dictionary here. So first keyword is category. So I'm going to set that to COM for commissioning and ERS for those early release science observations. Next, we're going to set the exposure type. And as I mentioned above, we're looking for nearest observations. So I'm going to specify NIS for nearest, and then I'm going to add underscore SOSS. So that's single object slitless spectroscopy, which is the type of observation that we're looking for. Next, TSO visit. So we just talked about this above, that we're searching for time series observations. So is this a time series observation? True. And finally, we're going to set the date. So that's the keyword here is date, obs, MJD. And then for this, we're actually going to use that first helper function. So I'm going to say set MJD range. And again, this is just the name of the function we defined above. Start date is going to be June 1st, 2022. And our end date is going to be the 8th of August. I'm sorry, the 4th of August of 2022. Now, why this date range? Because it's arbitrary. You may have a legitimate reason to do this if you were looking for some particular astrophysical phenomenon, some sort of transient thing. That could be why you might genuinely want to set this. We're doing it partially as a demonstration and partially just to limit the number of results. So there's no significance here. You don't need to worry about that. All right. So we've gotten our keywords set up in this nice dictionary, and now we're actually going to use our other handy dandy function to set our parameters. So again, I'm going to make a new dictionary, and this is what we're going to pass to our API. So the columns that we want it to give back to us are all of them. And the filters, right? The filters that we want it to search on. Well, okay, the syntax here is a little weird. So we're going to use our helper function again, set params, and we're going to pass it the keywords that we just wrote above. And I will close that and run it. Now let's take a look at what we've actually done here. What are these parameters that we're passing? So I'm going to print that out. And you can see this is the final result of what we're going to be searching on. So we want all of the columns returned, and then here are our filters. And you can see this parameter name value syntax I was talking about earlier. You can imagine it gets fairly tedious to type this out when you have to say parameter name, category, values, COMERS, parameter name, exposure type, and so on and so forth, right? It's a lot of typing. So these helper functions are pretty handy if you do plan on using this less user-friendly version. Okay, so we've gotten our keywords set up and our filter criteria. We have formatted this query correctly, which again, if you want to see more about this, you can follow these links up above. And now that we have this, we actually need to execute the search. So that's what we're going to do. We do need to tell the API which MAST service we want to use. So that's what I'm doing right now. I'm saying we're going to set the service to mast.jwst.filtered.nearest, because that is going to give us our JWST nearest data back. And then I'm just going to create a table to hold its response. So T for table, and we're going to do mast.service request. We need two things. We need the service, which we just defined above. And then we need params, which again is this special formatted thing that we were working on building. With that, we can run it, and down below there is some data in this table that makes it somewhat difficult to display and actually look at during a demo. So we're limiting the columns that are being displayed, and we're also just going to look at the first 5 of them. And actually, that query that has already executed, so it's very fast using this to search. You'll notice there's a lot of information in this table. There's file name, file set name, product levels, and in fact, I think this table actually goes quite far. It's very information dense. So I'm not even going to try to scroll all the way to the other end because I did that yesterday and it took me a lot of time to scroll back. But what we've gotten back here in our results is this list of files, right? Each one of these has a file name, product level. There is a direct data file associated with every entry in this list. Part 2, doing an observation search. So first of all, we need to address what are we doing and why are we doing this? As I mentioned earlier, that MAST class unlocks for us a very powerful type of search that isn't necessarily available in other search forms easily. So with that, we have our list of files that have been returned. But we might not be looking for these particular files. We might want to get at some of the lower level files, because as I mentioned, those level 1 files are not going to be available in this search. And it might just be good for you to take a look at the actual observations that are associated with those files. So what we're going to do is we're going to derive the observation IDs from these file names here to find the corresponding JWST observations in our database. And the reason why we're doing this is because if we want those lower level files, we need to perform a search in the multi-mission database. And so the difference here, again, and really to reiterate this, is that one of these searches is searching for files, the other is searching for observations, which are collections of files associated with a particular telescope pointing in the sky. And so our general flow through this is that we've used this filtered nearest query in the astroquery.mast, the MAST class, to get our file names. We're going to convert those into observation ID metadata, which we can then search on using the multi-mission database and this observations class that searches it to get back that list of observations. Okay, so let's jump right into that then. In this particular case, we can get the observation ID by removing everything in the file name from the final underscore to the end of the file name. So let's do exactly that. And to get started, what we need to do is create a list of our unique file names. So let's get the list of the set of unique file names, which is in our table above. And the name of the upper index there is file name. Okay, so this is going to get us a list of unique file names from our above search. And then there's a bit of magic happening down here. You don't need to worry about this too much. It is the same thing as sort of chopping off that data product type from the file names up above. So I'm going to print out the IDs that it's given us, and we can do a quick comparison. So this is the observation ID. And if you take a look at these file names up above, you'll notice, right, it has a very similar structure. And all we've done is cut off this last bit right here, this rate int.fit or this rate.fits or ramp.fits or whatever it is, right? We've cut off that part to get at the overarching observation ID. And this is our list of observation IDs. And actually, that's quite a lot of them. So let's just do the first 5 to not clutter things. Okay. Now that we have these observation IDs, that we have actual metadata about the observations, we can use the observations class to perform our search. Okay. Let's do exactly that. We're going to say that our matched obs are, and we're going to do observations dot. The function we're using here is query criteria. And the fields that you can give query criteria are described up above in this link. So again, after the webinar, please feel free to check this out. The ones that we are going to set are instrument name equals nearest Okay, this is probably the most important thing I'm going to tell you in this notebook presentation. So if there's one thing that you write down, if there's one thing that you remember, let it be this. I am putting an asterisk after nearest. We need a wildcard character. Why do we need this? We need this because it is not enough to specify that the instrument name is nearest. You need to specify the instrument and the configuration. If I were being specific for this particular search, I might specify nearest SOS, single object slitless spectroscopy. But if you just wanted to search for nearest in any configuration at all, you need that asterisk or you are going to get 0 results. You can imagine that would be particularly devastating if you were using this, for example, to do duplication checking, or if you were trying to find your results and you were going, it looks like none of my results are showing up. It is very important that you put that asterisk there. Okay. The next criteria we're going to add is opt ID, which is that observation ID that we talked about, and we're going to use our IDs from above. All right. And again, we have this little magic down below to limit displaying our some of the information in this table that kind of clutters it up. What we're looking at now is a table of the observations. So these are those, again, there was a particular pointing of a telescope, it looked somewhere, it took a measurement of some kind in a particular filter with a particular instrument, and this observation sort of holds all of the relevant data from that. So it's the science observation, the calibration files that are relevant. In the case of JWST, there are quite a few GuideStar files that are associated with each of these, but these observations hold all of that information within them. And now as a quick test, this is just good practice. It's not necessary here because we printed out the table and we can see we have results, but you should just make sure, am I actually getting results back from this query, or else things are going to go poorly for you. These next steps will fail. So I'm just asking it to print out the length of the matched observations. Whoops. Chain obs. Okay, 16. So there are 16 matching observations. So this is good. We're not going to fail on our next steps. Part 3, actually querying for the data products. So as I was just sort of alluding to, right, these are observations. These are objects that are meant to be the overarching idea of that telescope pointing somewhere and taking data, but there's many individual files that are underneath each one of these observations. So what we want to do is get back those files that are under the overarching observation. And to do that, there's a handy function that we can use. So let's get our data products, and we're going to get them using observations. The function is get product list. And what we need to pass it is our table of matched observations. You can also pass it a list of observation IDs as well, instead of a table, if that's what you prefer. So that query, we just ran that query, and we should actually take a look at that really quick. So let's take a look at what it's getting back to us. Okay, these are the first 5 products that come back to us, and you can tell that these are now actual files, right? We're back to our x1d inst.fits and stream.fits. So we've sort of come full circle, except now we have access to files that we didn't have access to before. And for example, you can see this last item here is a GuideStar acquisition. That is not accessible to you using the first type of search that we did. Okay, let me clear that out. In this particular case, we don't want those GuideStar files, so we're going to create this filtered products variable to hold our filtered products. And the command to filter them down is actually, it's pretty intuitive. So it's observations dot filter underscore products. What we need to pass to this is our products from before, and then the criteria that we want to filter on. So in this case, we'll do product type equals science science and info. So this will exclude some of those calibration things. This is going to exclude, for example, guide star files, which I just said we don't really want. So this can help narrow things down quite substantially. And actually, I think let's keep a different comparison in our minds. So the length of the products without filtering, 3,499. That is a lot of files. So let's see what happens once we filter stuff down here. I'm going to set the calibration level. I'm actually going to set it to 1. I know if you read up above and in the comments it says 2 and 3, but I've been talking so much about how this search allows you to get to those underlying level 1 files, so we're gonna focus on that. And I'm going to set one final thing. This is a whole can of worms that we maybe don't want to get into right now, but I'm going to set MRP only, that's minimum recommended products only, equal to true. What that's going to do is it's going to select the list of files that are considered essential to doing your science, but they're considered essential by MAST. And we cannot anticipate every possible scientific use case for the data that is in our archive. So you may find that by using this filter, you're actually removing particular sets of data that you're interested in. So then you might not be able to use it at all. For most cases, you're probably fine to do it, and it does help to, again, continue to trim down the number of files. So we're going to use it in this notebook. And now let's take a look at what we've got and what we filtered this down to. So with our criteria, you can see the only thing that we really have is this uncalibrated 4D exposure data, all of these uncal.fits files. And I actually don't think we're displaying the full length here. So let's see the length of filtered products. Keeping in mind, before I hit enter, we started with 3,499 products, and we are filtered down to 13. So this is much more manageable if you're trying to get at a particular type of data. You can really narrow things down using these criteria. All right. Before we actually do the download, I do want to do a brief aside about downloading the data products if you are working with proprietary data. There are two things that you are going to need to be able to download this data. You're going to need to be authorized, and then you're going to need to be authenticated. The first of those, authorized, that can only come from the PI of the program. So you need the PI to authorize you looking at this data and getting access. Once you actually have your authorization, because you're on the program team, you then need to be authenticated. So that just requires creating a MAST account, which is free. All you need to give us is your name and email so we can contact you. And then you'll get an auth.mast token, which you can generate by clicking on this link here, and you just can provide it to scripts. It's actually as simple as running this observations.login command and then passing your token to it, and it will authenticate you. We're not going to do this here. It's only necessary if you are retrieving proprietary data, and we are not. We're just looking for public data. Just for those of you out there who might need to do this, this is how you would go about this. All right, let's actually get some files. I'm going to demonstrate two ways to do this. So the first, we're going to use a bash script. So I am going to call observations.download products. This is what we're going to use both times. Products. We're going to give it our filtered products. Then I'm setting something kind of special here. So I'm setting curl flag equals true. What this is going to do is when I run this, it is going to not download the products. It is going to instead download a bash script that uses curl that will allow you to run your download at a later time. Now, why would you do this? Why would you just not download it directly? Well, two reasons. If you have a large number of files, so I mean, if you have more than 100, if you have 1,000 files, I would definitely recommend doing it this way. Or if you have, if the size of those files is large, so if you're downloading tens of gigabytes of data, this might be the better way. The reason is simply that curl is generally a little bit more robust against download interruptions than simply trying to stream the data. So if your internet connection is a little bit weaker or tends to go out, Or again, if you're just downloading a lot of data, this is the recommended method to get this to your computer. So I'll run this really quick, and you see it. It was almost instantaneous. It just downloaded this bash file, which you could run by opening up a terminal and typing bash and then the name of the file. We're not going to do that right now, but it is a very powerful tool that many people underutilize. Okay. Let's proceed to the other way that we're going to do things, which is the same call. So that's observations.download products for our filtered products. But I'm just going to do the last one because we're not passing a curl flag. We're actually going to do this download, and I would prefer to not crash our servers by having 20 people simultaneously try to download a bunch of files. So we'll give it this first one to download, and it's already finished. We chose a pretty reasonably sized file for this demo. Now you actually have the data. Here's where your real science begins, but it felt wrong to just end this without actually doing something with the data that we've spent all this time trying to get. So we're just going to open it up. So what I'm doing right now is I am using the fits.get data, and I am passing it the location of this file, which we should actually take a look at once I get to the end of this line. If you take a look at this manifest that I've been using to hold the output from download products, you'll see we get a table back, which contains the local path, the path to the file we just downloaded. It has the status, which in this case is complete because it succeeded without error, and then message and URL. So these are currently none because nothing went wrong. If something had gone wrong and this had failed for one reason or another, you would get a message telling you, why. But ours was successful, so we don't need to worry about that. All right. Let's continue. So we've just opened up the data. I'm just making a figure to plot this. And we're going to do an im show for this particular slice of data. Oops, what did I? Oh, big sure. I don't think so. Big size. And here we go. So we're seeing this kind of raw readout from the detector. And there is quite a bit of calibration to be done before this is actually a useful scientific product. But that's what we get, right, for going straight to the level 1 products. But it is kind of nice that you can sort of dive right into this and understand where it's coming from in the instrumentation. Search form. So this JWST search form is sort of a modernized JWST specific version. If you've been performing your JWST searches this way, I recommend when this new form comes out, you give it a try. It's meant to be pretty powerful and pretty user friendly. So with that, let's jump right in. Let's select our mission. So in this case, we're searching for web, and that opens up the search form, which is very similar to the Hubble search form. And what we're going to do, our target for today's search is we're pretending that we are the principal investigators, and we are trying to get our data out of this. Step one of this, we could search by the PI surname, so that would be as easy as typing your own name into the field or your one of your co-investigators' names. But in this case, we're just going to use the proposal number, which is, I think, just as easy. So our proposal in this case is 2420. We'll let that sit there for just a second. I appreciate that this may be pretty small, so if you can't see this, don't worry about it. You can explore this outside of the webinar, but at the very bottom down here, it's giving us the number of filtered results. And that number is updating live. So just when I typed in 2420, it brought the filtered results number down to 18, which is pretty handy that you can see the effects of what you're doing before you even press search. I think it's pretty nifty. The other field that we're going to search on, since we've already narrowed it down to our program, what we're also going to do is narrow it down to a particular filter. So within this, and for everyone who's in the Slack, I think Dick just sent a link to the version of this search form. Again, note this is a test. If you play around with it, feel free to go ahead and play around with it, but it is not feature complete. There are still things we're working on. For example, you can't type in a visit number within a program yet. So don't expect everything to work, but please do feel free to try it out. At any rate, the other field we're going to use, like I said, is the optical elements, which we can use to type in a filter. And what's pretty neat about this is if I start typing, if I type in F, I get a list. This is an autocomplete list of the fields that I can enter that are valid for JWST. So I'll start typing. I was thinking of F1, and there it is. That's as far as I have to type. This is the filter that I wanted. And what's also very nifty, I think, is when you click this, it turns green. It turns green, you get a check mark, so you know that you have entered a valid filter for this. If, for example, you were certain that you requested it be observed with F999Z, you can see that you must be mistaken. It turns yellow, you get one element does not align with instrument selection, so it's trying to tell you, hey, the filter you've entered isn't a real filter, and in fact, it's not going to search on it. If you don't get this green box, it's letting you know that it's unable to search on your criteria. And that actually applies to some other fields on this form as well. All right. With that, there's a whole bunch of other stuff on this search form that you could try out. Evidently, we're not going to get to that right now. The one last feature I want to show you before we actually hit search is the Show API Query button. I just think this is so cool. So if you click on Python, it will generate a Python script that will search for everything that you have put into the search form. So you can see I only had 2 criteria, right? So, well, there wasn't a whole lot. But filter equals F110W and program is 2420. It's pretty neat. I think it's cool both for those people who, if you don't have a whole bunch of experience with MAST and our APIs, the search interface is the most user-friendly way to start. And this sort of helps ease you into the programming side of things. It's also great as a teaching tool. We've had some professors who say, "Oh, I wish my students knew how to program and could actually use your APIs." And we say, "Well, now it's as simple as clicking the Show API Query button to help them get started with that." So, I just really enjoy that feature. I just shout that one out. All right, but let's actually perform our search now. So, this search form is pretty quick. And as a note, if you have ever used the portal, there's a hard limit on that of 50,000 search results. This search form has no such limitations. As a matter of fact, I think as an experiment, we just tried a blank search, and it took it a little bit, but it did return all of the search results, I think, after a minute or two, which is pretty impressive for nearly 1 million observations. Okay. As before, when we were searching on observations, we have this overarching observation result that's been returned to us, but there's not actually, we're not actually looking at the underlying data here. So to get to that, we're going to need to select some of these and go into this download data menu. You could choose to just do a quick download and get all the files or just the recommended files. I'm going to choose them individually so I can show you this menu here and take a look at some of those features that are in there. Now, as I mentioned, this is still the test version. It is not feature complete. So this is going to take it a little while to spin up and actually find these files. This is not, I repeat, this is not the behavior that you should expect when this search form actually goes live. One of our priorities for this search form is making it accessible and responsive and easy to use. And if you kind of have to sit around and wait for one observation to load in, that detracts from that experience. So I just want to be clear that this is not what things will be like when this is actually released. This same thing happened yesterday. We had to wait a little bit for it to actually load these files in. So while we're waiting, I'm going to just talk about some of the features that you might sort of be able to see behind this loading screen. And if not, don't worry about it. I'll try to recap as best I can once it becomes available. Some of the things that you can do here, as with some of our other search forms or with some of the other concepts we've talked about, there's the option to download everything. all with no filtering. You can do recommended, so you can get those minimum recommended products, or you can select none. Now, these options here just allow you to change what's selected for download. At the moment, you can see up at the top, we have 0 megabyte 0 file selected because there's nothing. It hasn't loaded yet, so we couldn't have possibly selected anything. But of the files that we're trying to load in, there are 23 files totaling 250 megabytes that are available for download. Now, within this file selection, one option of a filter that we can apply is the levels of data processing. So that'll let us select between levels 3, 2, and 1. Yes, it loaded. All right. I talked long enough. That'll allow us to select between levels 3, 2, and 1. And in this case, I picked an example that didn't have level 3 data, but that's all right. You can still see that we have the ability to select underneath, right? So I can get down to level 2A, 1B, 1A. And if I open this, each one of these only has one file type underneath. In this case, this is rate, this is on cal. But these often have multiple underneath. So there might be multiple 1A, type 1A files or multiple 2A type files available for you underneath this. Okay. The other thing that we can do is choose whether or not to include GuideStar files, which includes a lot of stuff. So we're not going to do that here, and it doesn't actually make a difference in this selection menu. But I'm going to go back to none because you can because we don't need them for the purposes of this download. The last feature that I am going to shout out here is this using regular expressions to choose file names. This is super, super handy. So if you're looking for, in particular, let's say that those rate ints types of files, you could select them from above, but you can also just come right here, type rate ints .fits, and actually I don't even need the .fits, right? It's already, you can tell up at the top, it's already found the one singular file that matches this. And just note that since we are using regular expressions, normal wildcards wouldn't work. So if you, for example, if you put this asterisk here, this is going to go to 0 files. I just recently made this mistake. If you actually want to wildcard it, you'll have to use the regular expression syntax, which would be like .star, for example. But because we allow regular expressions, you can get pretty particular with the types of files that you actually want to download. Right. And you know what? I'm actually going to put that rate ints back in because it'll give us one file, and that'll be good for us to download. You can view all the selected files that you're downloading just to make sure that there's nothing in there that you don't want. You can see this full list here. And then the last feature that I am going to shout out is this file structure option. So we've only selected one observation, so it's not going to make a difference in this case. But if you have selected multiple observations, the current default behavior in the vast majority of our search interfaces, I struggle to think of a counterexample, is nested. So when you'll get a download folder that'll be MAST download with some timestamp on it. And within that download folder, there are additional folders for each dataset ID, or as we often call them, the observation ID. So under each one of those, you'll have so you got a whole bunch of folders. Under each one of those, all of the associated files are organized. So it is nice in the sense that you can browse the file tree, but if you're trying to do something programmatically, it can be somewhat irritating to have to programmatically browse a file tree. It's not quite as easy. To that end, you can just select flat. So instead of downloading everything into separate directories that are separated based on the observation ID, it dumps everything into just one singular directory, which does make it a lot easier for you if you're trying to access this kind of stuff programmatically. We've sort of arrived at the end of this, so we can hit start download. That zip file has just begun its download. You could instead do an API query, which will allow you to get a curl script as I was talking about earlier to complete this download.